So next we're going to look at the concept of atomic mass and natural abundance. So the atomic mass of an element represents the average mass of its naturally occurring isotopes that make up the element. So the idea behind this is that since you can have multiple isotopes, you have a different collection of things, so different ones actually have slightly different masses. But to do chemistry, many times we're working with large numbers of these atoms, and we don't need to know, okay, are there 24 of this type of isotope or 25? So instead what we do is we work with an average mass for that object because that works with really large samples. So that shouldn't cause significant error. We're going to go with the idea of carbon, maybe a mixture of carbon-12 and carbon-14 or carbon-13, but we know it's average between those, and we can use that for doing problems in this class. This is important to remember that isotopes are not equally represented, so it has to be taken into account in the calculation. We can't just average the mass of each one, but we have to account for how much of a natural sample will be each isotope. This naturally occurring amount of an elemental isotope is also called its natural abundance. So let's take an example for neon. Neon naturally occurs as neon 20, 21, and 22. And the variation between these is oh, that's not plugged in. That's why. My pointer thing wasn't plugged in. There we go. Now I can draw. It's trying. Let's see if it can find itself. There we go. I turned it off of pin instead of onto. So the idea is the variation is caused by the difference in neutrons here. So what that means is that that's the only major difference, but we do know neutrons have mass. So a neon with 12 neutrons is going to have more mass than a neon with 10 neutrons. But the neon 20 with 10 neutrons is by far the most abundant. 90.48% of all neon will naturally be neon 20, whereas only 9.25% of it is going to be neon 22. So we need to figure out how to account for this when calculating mass. So let's take a look at this now. So the atomic mass is found by averaging each isotope and multiplying it by a fraction that represents how much of the isotope occurs. So what does that mean? How do I do that as an equation? So since atoms are small, first off, we're going to use a different unit that we haven't talked about yet. It's called an atomic mass unit. So this is a mass that's going to be reasonable for talking about things where we're at single atoms, because single atoms are very, very light. So in the last slide, we knew that neon 20, for example, was 90.48%. We also know the masses of these things. So neon 20 is going to be about 20 AMUs, not exactly, but about. And then neon 21 will be about 21, and neon 22 will be about 22. You can also work with more exact numbers, and we'll do a problem next with that where we work with really exact numbers for the AMUs because the proton and neutron don't have the exact same mass. So that can come up and there's slight variations. So how do we calculate this? So what I did was I took the atomic mass, and I took my 90.48% and I turned it into a decimal. Remember, when we've got a percent sign here, all we do is we move the decimal 2 times. Similarly, 0.27% means that we would need to move the decimal 2 more times. So we have another 0 there, so it'd be 0.0027, and that's what shows up here. And then our 9.25, since we had to move the decimal twice, we had to add an extra 0 to account for that additional move, and so we get 0.0925. We multiply each of these by their mass, and we add them up, and we get 20.19 AMUs. You may also see this written as a summation sign, which is just a fancy way of saying add up all the things in the group. And what you do is you're adding together the proportion of the isotope, that's supposed to be V, not T, of the isotope, times its mass. So that's what each of these cases was. The proportion of the isotope is how much of it is there. So in a sample, 90.48% can be rewritten as a decimal as 0.9048. And then the masses were 20, 21, and 22. So that got us our mass. It's also possible to look up the natural atomic mass for an atom by looking at a periodic table. The atomic mass is the number that occurs directly below the symbol. So for example, if you were to look up the element hydrogen, it would have a 1 up top, which that 1 up top would represent its atomic number. And then down below, it would have its atomic mass, which might be something like 1.001 or whatever number you find there. You may notice, depending on periodic table, very slight differences. There won't be significant ones, but there may be some discussion with over time. Scientists may measure a little bit more carefully and may decide that like a third or a fourth decimal changes a little bit. Maybe we learn the number a little bit better. But it's not going to change. Like the first digit isn't going to change. We're really confident hydrogen weighs 1. Great, 1 AMU. But it's the question of, what does the third or fourth digit weigh? Over time, as we do more, look at more natural samples, that might change very slightly. In the case of neon, we did a bit of rounding for the mass. Oh, sorry, let me get this out of the way. There we go. Go away, Mr. There. There we go. Now we can read. So we did a bit of rounding for the mass. So the actual mass is 20.18 AMUs. So that's what I meant by there is technically some variation. It's not exactly 20, 21, and 22, but it is really, really close. Also, as an aside, for the purpose of solving problems in this class, I will sometimes work with problems that that don't use the natural amounts. So that means you can't just look up the number on the periodic table and get the answer there. You will actually have to solve one of these at some point. This is also relevant as there are times where we will have samples in a chemistry lab that for some reason would not have the same abundances as you would get in nature. For example, you might be working with a sample that came from space. This worked in my own graduate school lab, where some of the other people I wasn't directly working on it were working with things from space, such as meteorites that had landed, or there was a comet trail that they sent a satellite through and they got a piece of that. So when you're working with those samples, the distributions in space are actually different than in Earth. So in their case, when they needed to know how much of each isotope there were, their amounts weren't the same as what you would normally get on Earth. So it's not just something we do to make you solve a problem. There really are times where you work with samples where there might be differences there. You might also, for example, a biologically focused example, I don't want to say it's just space, would be different types of plants will process carbon slightly differently. So carbon isotope ratios change slightly based on whether the type of plant and how it deals with carbon fixation. So that means that you can get some variation in your isotopes there too. It's a really tiny change, but it is a change that is measurable. We can actually use it to try to figure out things like diets of people that lived a long time ago based on what the carbon is, how the carbon is set up, like what the distribution of it is. So there are times this comes up. So having that aside, let's do a practice problem. So I want you to try this one. Naturally occurring magnesium occurs at these percentages for these 3 types of magnesium. Try finding what its atomic mass is. And that means pause me and give it a shot before listening to the rest of this. Okay, let's take a look. So we want to do our atomic mass for magnesium. So first we're going to start with, we have 0.7899 is the fraction of our magnesium that's magnesium 24. And it has a mass of 23.99 AMUs. We're going to add to that 10%, or 0.1000, it has a mass of 24.99 AMUs. And then finally our third one is 0.1101, and it has a mass of 25.98 AMUs. So if you were to multiply all those together and add together, you will get that this has a mass of 24.31 AMUs. A good sanity check on this answer is it is by far the closest to the mass 23.99. And since 79% of the magnesium is that mass, it makes sense it would be close to that. Because only having 20% that has a larger mass means it's not going to pull us for as close to those. It would be strange if you got an answer like 25.8, since only 11% is magnesium 26. So that's a good check that sort of it reasons out and makes sense that this would be the answer to this. So the last thing I want to do in this particular small presentation is talk about where some of this information is located. I mentioned before that you could get a number at the bottom of your atomic mass. So here is a picture of our symbol, and so we would work with. So you'll always have so as a reminder, you'll always have this atomic number on top. You'll have the elemental symbol here. Depending on the periodic table you're looking at, many of them will have the name here, hydrogen. Some won't have the name, but many will. And then you'll have the atomic weight or atomic mass at the bottom, which represents the average mass of all hydrogen that naturally occurs on Earth. So the number at top, remember, is also, as a good refresher, it is the atomic number, which we use the symbol A to represent. It's important to remember that that number does not directly tell us anything about the number of neutrons. So anytime you have a question about how many protons your atom has, if you know the type of atom it is, you can go to the periodic table and you can find out what number's up there, and that number is how many protons do you have. And then also the symbol can help out because you may know it's the word hydrogen, but you actually want to write it as a chemical formula, which we'll work on later in the semester, or you're just looking at something that just has an H. By looking at the periodic table, you can find out what does that symbol stand for. So for example, one that you might know is, for example, gold, which Considering hydrogen starts with an H, gold, why doesn't it start with a G? Well, gold is actually represented with the term Au. And so by looking at the periodic table, we could see that and not just look at Au and be like, what is that? Which is related to the word auric. So it's there's a reason it's Au. It's not just, well, we thought gold would look good as Au. There is some reason behind each of the lettering setups with them. So at the bottom, we have our atomic mass. And atomic weight, you're going to hear both those names used interchangeably. As we go throughout the semester, that number on the bottom will get used a whole lot. You will get used to looking them up. You will be doing it on probably every single chapter from now on, and you'll be doing it on multiple problems throughout your quizzes and tests. You're going to be looking for that number a lot. It's good to learn where it is. So we're going to also discuss in a later chapter why the periodic table is arranged in the shape it is and why all the information is where it is. But for right now, we're just going to say this is the information we can collect here. And we're going to do more on it coming up in the next chapter or two.